Okay, we're going to do some more statistics today. So we're going to look at the normal distribution again, the t-distribution, and coding. So how can we use Python to code some solutions to those type of problems that deal with normal distribution and the t-distribution. We're also hopefully going to get to strain gauges. Here's a strain gauge in this little package. This is a kind of like a load cell. It's a little force sensor underneath these, underneath this, and I don't know if you can see on the bottom, but there's one on the bottom too. There's a similar, but I guess smaller because it looks like it wouldn't, well, I don't know, maybe it's the same size. Strain gauge underneath there and under the bottom here, and this is a little scale, so we can use it to figure out the weight of something once it's calibrated. Right now these wires are going over to the Arduino, and it's got some code running on it to measure this strain gauge. This little chip right here is a HX711. It's a particular chip that helps with measuring the strain gauge. The way these work, we'll talk about these later, but they again change their resistance. But this time they change the resistance with strain. So as they strain, either they get longer or shorter if the beam is in tension or compression. And they will change their resistance, and we can pick that up. We just need, it's a very tiny, we had the, where'd it go? We had the thermistor, which changed its resistance based on temperature somewhere. We also had a photoresistor. I think I've lost that temporarily. No, wait, here it is. We had a photoresistor. Changed its resistance with light level. This guy changes its resistance with strain. So as strain increases or decreases, then its resistance will change. And so you can kind of see a theme here of changing resistance that we need to measure. And so this HX711 helps with that. We hopefully, we'll get to it today, are going to build our own little load cell out of a piece of aluminum strain gauge. We won't need these. Although I will say the thermistor might be helpful because these are sensitive to temperature changes also, because temperature can cause the base material to expand or contract. And so there will be strain induced just from temperature changes that are not related to the weight that it's experiencing or the force it experiences. But we're going to ignore that for now. We're going to get this guy on here mounted, and we won't get to measure today because we have to do some other circuit. We have to basically build our version of a very simple one of these. We're going to build a Wheatstone bridge. I don't think we'll get to that today though. I didn't get all the stuff out for that. We'll do that later. Hopefully today we can just get this mounted and hook it up to our multimeter and actually see a change in resistance. But before we do that, let's go over and let's go to Thani so that we can do some coding. And what we're going to try and code here is some computer solutions to some of the same things. We'll do them by hand again also, but where you use the standard normal distribution chart, one of these guys, get it over here, one of these guys, and how can we make the computer through Python do this same process? That's what our goal is. First thing I think is, very first thing is we need to install a new library. So we need to, you probably don't have this one already installed, manage packages. I'm in Thani over here, manage packages, and you need the SciPy package. And it looks like we're on version 1.5.2 right now. I already have it installed, so I don't need to, but you would need to install this because we're going to use some libraries inside, or some functions or methods inside SciPy that let us do the statistics. And so we need that. All right, so how about we get this started by just trying to plot the standard normal distribution. Let's draw what we're going to plot first. So what we want to draw, or what we want to plot, is, I'm just going to draw as an axis here, and then we'll put, let's put 0 right here. So this is 0. So this will be a mean of 0, and we want to plot this guy. So a standard, hopefully it's symmetric. The computer will do a better job of making it symmetric than I did. And then we're going to have a standard deviation of 1 in this. So we're going to have mu equals 0. We're going to put the average at 0. And we're going to have standard deviation equal to 1. So if we went over to 1, plus 1, and then 2, minus 1, minus 2, minus 3. These are standard deviations along the bottom. So plus 1 standard deviation, plus another standard deviation, and plus a third standard deviation. This area here that I'm going to shade in blue, that represents 68% of the area. So 68% of the total area. If we add this to this, so I'm going out plus or minus 2 standard deviations from the mean. The red plus blue rather, not just the red, but the red plus the blue, that's going to be 95% of the area under the curve. And then if we add that third standard deviation, whoops, we'll make it green. This will be green plus red plus blue. All of that area under the curve is almost 100, but it's not 100. It's 99.7%. So that would give you 3 standard deviations in either direction. Will give you 99.7% of all possibilities according to a normal, standard normal distribution. And you may have heard of the term 6 sigma when it talks to maybe some industrial engineering or some lean manufacturing or things like that. This is 6 sigma. There's 1, 2, 3, 4, 5, 6 sigma, so 6 standard deviations, plus 3 on one side of the mean and minus 3 on the other side of the mean is 99.7% of the area under that curve. We want to plot this thing. So let's go over to Thani again. And let's just, well, actually we need some libraries first. So let's import. We need our matplotlib because we're going to make plots. Matplot library. We only need the pyplot part of it. And we've been importing it as PLT, so we'll keep doing that. We need NumPy. We use that one a little bit. So we need that. We're just going to import it as NP. And then our new one, SciPy, we only need the stats part of that. And we're going to import it as SP. So we have 3 little libraries that we can access to plot and do some statistics and do some numbering issue things, make some axes, stuff like that. Let's say that our mean, let's just use, I'm not going to try and put a mu. I guess you could spell out mu if you wanted to. Let's just use M equals, we're going to just have a list right now of 1. We can make it have more than 1, but let's just say it has 1. And it has a standard deviation of, whoops, I did those backwards. No, that's right. I want the mean at 0, standard deviation of 1. All right, so that's just it. And these variables could be named whatever. You could actually type out mean and standard deviation or whatever. They're just variables. I'm just using them as placeholders for the 0 and the 1. All right, and we have our libraries imported. One thing we need to do is we need to use this NumPy library to create an array of numbers. So let's just call, this is going to be the x values along the bottom down here. We could make exactly the ones I labeled, but I'm going to make I'm going to go from let's just go from -6 to 6. So how we do that is we'll just call it variable x, and it's going to equal, there's that NumPy library, and then line space, or whether it doesn't have an E in there for line, but lin space, I guess. We're going to go from -6 to +6, and we're going to evenly space 100 points in that range. So this will give us I don't know what the actual numbers will be, but anything from -6 to 6, and it's going to divide that range into 100 equal sizes and put them into this variable called x. Now we need to create what's called a handle for the actual curve here. So how we do that is we just call that n. Doesn't matter what the name is here. Here's the SciPy library, and it's a normal distribution. So this is a function in the SciPy library, and we want to create a normal distribution that has a mean that we specified, so m, and I guess technically m0 since we made it a list, and standard deviation. So we could have put 0 and 1 in here if we wanted to, instead of calling this list. But the idea here is that we could go back and change these to other means and other standard deviations, and it would change it out here. So this isn't equal to 0. This is the 0 index from this list. So if I had 0, 1, 2, if I had a whole bunch of stuff in this list over here, then it would, whoops, we don't need that comma though. It would pick the first one, right? It would pick the one in the 0 spot. Same thing for standard deviation. It would pick the one in the index 0 spot, which is the first one. All right, so now I have an axis, or at least the numbers to create an axis on the x direction, and I have created a normal distribution that has a mean of 0, standard deviation of 1. So I have that. Now I want to plot it. So this is the same thing we've been doing where we create our figure. We only need one, right? So we'll just put one row, one column, and that'll give us one graph on our figure. And then we can make the titles and labels. I'm not going to worry with all that. I don't know if we've done this. So this is the axis horizontal line. We could color those particular colors. K is black, B is blue, so we can't use B for black, we have to use K. You see that other places too, like CMYK is a color space, the K in there is black. So a lot of times black will be K. So this just makes this axis and this horizontal and vertical, it makes them black. So you could color them whatever color you wanted. Now let's create our plot. And we're going to plot x. So x is this variable, right? And we're going to plot, for our y-axis, we're going to plot n. So all the normal distribution that was created around the mean and standard deviation that we set. We could give this a different color. Blue, so B is blue, and if we put a dash behind it, it'll be a solid line. I don't remember all the codes for dotted dashed lines and everything, but there are a lot of different codes. We looked at those earlier. We can make it a certain line width if we wanted to. So maybe line width of 2 or 1 or whatever you wanted. We could put labels on there if we wanted to. I think that's all that we need to get it. Well, actually, we could just do x comma n, and that would plot it. This changes the color and the line width is all that does. And then let's plot, or show the plot. We'll probably have to save this when I run it. Yes. Let's see, this is standard normal. I'll just call it that. Let's see if we get our plot. I have not. Uh-oh, let's see. Somewhere in here I've got a little error. Let's see if we can track it down. It says that well, actually these are errors in this axis library that got called from here somewhere. So it's in one. I sent the wrong parameters to one of those libraries that were called. Let's see if I can figure it out. Let's see. So we did, this shouldn't be a problem. This is just important libraries. This shouldn't be a problem. That's just declaring some lists. So that shouldn't actually create problems. Oh, you know what? I just put in here. I need to tell it what to actually plot here. So this is going to be in is referring to this normal distribution that we created, but I need to, there's several different functions that I can use to access this normal distribution. I want the probability density function. So that is the curve. That's this curve. So I want that, and I want it to be with x, which is that same range from -6 to 6. So I didn't tell it actually what I wanted. I just said in. So I needed to, there's several of these. There's CDF, PDF, and PPF, I think. We'll get to all of them later today. So let's try again. There we go. So there is, you know, a nicer version of what I tried to draw. Now what theirs is, it brings out a little bit more of the data. Let's actually change this. You know, when I drew it, I drew from -3 to 3. And when I plotted it, I plotted from -6 to +6. Let's change those so that they'll look at least sort of like what I did. So all we need to do there is go from -3 to +3 and rerun it. That's more like what I drew. It's not exactly, but at least it has the same idea. And you can kind of see where if you went from -1 standard deviation, where in this graph the standard deviation is 1, then -1 to +1, that's 68% of the data. And then if you went from -2 all the way to +2 standard deviations, again where the standard deviation equals 1, then you have 95% of the data. And then if you go from -3 to +3, you get 99.7% of the data. And then that first time when we ran it out from -6 to +6, you can see that there's not a whole lot. There's 0.15% of the data on either side after you get past 3 standard deviations. So there's not a whole lot of chance of things occurring outside of that 6 standard deviation window, from -3 standard deviations from the mean to +3 standard deviations on the other side of the mean. Most everything's going to happen under that curve. All right, so this is just plotting the curve. It doesn't actually do any of the calculations that we were trying to do. So now that we can plot it. So let's see how, and it always is good to me to plot it so that we have an idea of what we're trying to do. Remember, these curves, when we look at it from a chart point of view, they're talking about some area under the curve. And it's helpful for me to kind of shade in that area so that I can try and figure out, do I need to add another 0.5 to it or subtract it from 1, or what do I need to do? And so it's useful to draw these things out. All right, let's come. Wow. Hold on. Everything kind of hid on me all of a sudden. Shouldn't have moved it like that. All right, so we're back to Thani over here. And I think what we're going to do is actually, let's go and do one by hand, and then we will do the same thing but in Python. So what we're going to do by hand, let's do it by hand first. We don't need Python up. And let's see if I can find my chat again, because it hid itself. There we go. Let's say that if we have, instead of a mean of 0 and a standard deviation of 1, those aren't really, I mean, that could happen, right? It's totally possible. But that's kind of just a generic thing. Let's make some numbers that might be a little more reasonable. Let's say that we have a mean of 100 and a standard deviation of 37. So these numbers, if we translated them over to this chart, I'd have a 100 here, 137 here, 63 here. You know, I'd subtract and add one standard deviation, which is 37. Then I'd add another standard deviation, so 174 over here, and whatever number I'm at, I'm losing track of. I think that was 63 minus 37, so forth. So they get smaller and smaller and larger the further away from the mean that we get. In fact, we could plot this really quickly just by changing our, let's get rid of all these. It's probably confusing to have all these others out here. So we have a mean of 100, standard deviation of 37. Now we have to change our range. If we only go from 3 to 3 and our mean is 100, we won't plot anything. So let's change to, looks like we're going to go from negative, I don't know, 200, negative 300 to positive 300. We'll do it that way. See if that gives us a decent plot. There it is. All right, so there's our mean of 100, and then we go out positive 3 standard deviation. Well, actually, we went past it a little bit, but there's the standard normal distribution for the numbers that I'm describing here. All right, so these numbers. All right, let's see if we have this. What's the probability that a value of x equals, well, 75? We'll do that one. So 75 is, right in here somewhere on our chart. I wish I could draw a line. I don't have a way to draw on top of this, or do I? Let's see. Nope, none of those are a draw. So somewhere right around here would be 75, and I want to know what's the probability of a number of 75, and then I could do 75 or smaller or 75 or larger. Let's do 75 or less. So from here back, so I'm basically just looking at this little area being shaded in. All right, so on our graph, if we were to create a similar graph to what we created on the computer, there's 100 and 75's over here. I want to know this area. That's what I want to know. Now, slightly unfortunately, the standard normal chart that we have gives us area from the center over. So it doesn't give us quite the area that we're looking for in our chart here. It will give us actually this area. Now, this green area and the area left unshaded here, those are the same area. It's symmetric about the mean. So this and this are the same thing. So if I could figure out what the green area is, then I could take the 50%. So remember that from here over, that's going to be 50% of the area under this curve because it's symmetric. So I could 50% minus the green will give me what I've shaded in over here. So this is 100 minus 75. Oh, not minus 75, minus 25. So this number corresponds to 125, right? Because it's symmetric. So if I subtract off 25 from the mean, I get to 75. If I add 25 to the mean, I get to 125. And that'll give me this number that corresponds to this green area, which does look like what I've got in my chart over here. And not every chart does the exact same shading. So you have to make sure every one of these charts has a little picture like this that goes with it so that you know what area it's talking about. So what I need now is I need to calculate the z value that corresponds to this shaded area. All right, so we did z value once, maybe twice yesterday, but I doubt that you would remember the equation. Z equals x. X is going to be something on the x-axis over here. Minus mu over sigma. So x is 125. Mu is the mean, 100. Sigma is the standard deviation, 37. I don't know what that is, so we'll have to calculate that number. 125 minus 100 is 25. Divided by 37. 0.672 5 and 7. Our decimal, we only have 4 decimal places in the chart, so we'll use 4 decimal places here. So this is the z value that I need to find in the chart. Actually, the z value, we only have 2 decimal places. This is way more than what we need. All right, so we need to find a z value of 0.68 actually. All right, so let's look at our chart. And we have 0.6 here, and then there would be 0.68 would be 25.17% or 0.2517. All right. So, oh yeah, you can see that. So what I did is z, to find z, you go down to find the units place. If you have units, we have a 0 in the units place on ours, and the tenths place. So we have 0.6. So I'll go down to the 0.6, and then you run across the top to find the hundredths place. So I need a 8 in the hundredths place. So 0.6 and then 8 is in this column right here. So z equals 0.2517. I'm writing that down, 0.2517. All right. What that does is that says that this area that is shaded green is 25% of the area under the curve. So that means that this area over here, the symmetric one, the uncolored one right here, is also 25.17% of the area under the curve. So if I know that half, from the mean over, that's 50% of the area under the curve, I can do 50 minus this part. So this part is 25.17%. And that will leave this one to be 24.83%. So that says that there's a 24.83% chance that if I have a population with mean of 100, standard deviation of 37, a random number in that population would be 75 or smaller. There's a 25% chance of that happening. Now let's see if we can make Python do the same thing. All right. So let's get Python back up. And all this will do is plot it. So that doesn't actually do any of the calculations as far as figuring out if it's going to, give any particular percentage. But we can leave that up. There's no reason to change that part. So we'll leave that the way it is. All right, so we did it by hand. Let's code this in. So remember I said there was PDF is probability density function. There's a CDF that's cumulative density function. So that's the probability density function is basically the trace itself, the trace here. So if you give it an X value, the PDF will give you the Y value, so the height of that curve at any point. CDF, if I give it an X value, it will give the area under the curve from negative infinity over to whatever number you give it. So it's actually not giving the same exact thing that we calculated here. The standard table that we were using to do this by hand gave us from the mean over to the point. In Python anyway, the cumulative density function will give me from negative infinity, so way over here somewhere, over to, if I put 75 in, it'll give me over to 75, which is exactly what I want. So we're going to go, we can plot it, we can leave that alone and just add this at the bottom. So the probability is going to equal, we're using that same n, there's no reason to change this, it's still a normal distribution, we're still, and we've already coded it in to use our new mean and our new standard deviation, so it can keep that. And then we're going to use the cumulative density function, so CDF, and then we want to code in, I guess I didn't make a variable, we can let's just type in, let's just type in 75. I don't normally do the hard code in like this, I leave them as variables, but we could go and make our own variable if we wanted to and put it in there. So I think that's all we actually need to do, other than we need to print that out, right? Print P. So that should print it on our screen. So let's see if we got the same thing. All right, so it won't. So first thing, it brings up the plot. It won't actually print the P variable until we close the plot. So we close the plot, and there it is. Now it didn't give it to us in percent form. It gave it to us in decimal form. But there's 24.96. We had a slightly different number, 24.83. But that's just the little bit of variances in how the two different processes are being calculated. For one, remember, we had to round this number off to use our chart. We had to round 0.6757 to 0.68 was all our chart would work with. So we lost a little bit here, and you can see that little bit of difference in 24.83 versus 24.96. So it's still within reason, but do be aware that the computer, Excel, Python, whatever you're using, even your calculator, if it has statistical functions, they're going to work directly with the equation of this line and integrate under the equation, and a chart is going to not have that kind of resolution. So you're going to get differences, little differences, between what you do by hand and what you get in a calculator, and that's normal. That's okay. All right, so now we could do any number pretty easily with Python, just changing this number right here, this 75, to whatever. Like if we put 100, we should get 50%. And we get 0.5. Because that is the mean. So half of the data should be smaller than the mean. Half of it should be larger than the mean. Now you do have to remember cumulative density function, the one we're using here with the CDF. It gives you the percentage from negative infinity up to the number that you calculated. So it's not going to give you the same thing that the chart, at least the chart we were looking at, where it went from the mean over to whatever number you were dealing with. All right, what if we want to do, let's do one other type with this. Let's say that we want to calculate a range. I'm trying to look at my numbers here. All right, we might need a new page. All right, so let's just do different numbers so we can see how we code those in again. So now we have a mean equal to 42, so we've moved the mean over a little bit. Standard deviation, 7. So mean and standard deviation. We want to know the range that corresponds to 66%. So I'll tell you what that means in a second, or at least what I mean by that. All right, so let's draw. Again, I like to draw these. We could plot it in Python, but then I can't draw on it. So the mean is 42, and then we're going to add 7 to that for one standard deviation, so 49. Add another 7, 56, and then another 7 over there, whatever that would be, 63, I guess. And then subtract off 7. And that's going to be our something like that. Okay, and 66%. So half of it is right here. It should be symmetric. So that should be 50%. So 66% is going to be, we're going to guess. Let's do it in different color. I have green over here. So let's say that that's 66%. So what I want to know is from negative infinity to what number here is 66% of the data. That's what I want to know. All right. So if we were doing this by hand, let's do this by hand first. Let's look at our chart. So now we're kind of using this chart backwards. We're going to find numbers in the chart and reverse back out a z value. So let's find 66%. Well, no, we're not going to find 66% because remember, this chart only shows from the mean over, so at most it can show us 50%. So there's the 49.9. So we actually need, let's go look at our picture again. To make it look like our chart that's in the book, we need this area right here. And that area is 16%. 50 plus 16 is 66, right? So we need to find 16% in our chart. So we can actually find that one. Here's one right here. Here's another one. And here's two that span 16. So you'll end up with this a lot of times when you're using the charts by hand. You end up with needing to interpolate. So let me write down what we have on our chart. So at z value of 0.41, then we have 0.1591. And then a z value at 0.42, we have a value of 0.1628. Okay, so all I did is I just wrote down those so I can get to them in a second. So I need to interpolate because I want a value of 0.16 and I want to know what z goes there. So it's somewhere between 0.41 and 0.42, but I don't know exactly where. So we'll use our calculator and we'll interpolate between the two. Let's see, I don't interpolate a lot on this calculator, so let's see if I can remember how to do it. We need to go to mode. We're going to do some statistics. A plus bx, that's the equation of a straight line. We're going to do a linear interpolation. The line here is not linear exactly, it is curved. So we won't get exactly the same thing again that the computer is going to do because it doesn't have to interpolate between all these data points. It can find 0.16. So we'll use mode 2 here for a linear interpolation. That's the y equals mx plus b basically is what that form is. And we need to fill in this chart with x of 0.41 corresponds, let's go over to that spot, to 0.1591. And then over here, an x of 0.42 corresponds to a y of 0.1628. Okay, we can accept that. That's basically putting in the two x and y coordinates so it can do a linear interpolation between the two of them. Now what I need is I want to find 0.16. Where does it land between those two data points, assuming a linear interpolation? And to do that, I'd go to Shift Stat. I'm going to do a regression, so 5, and I actually want to find an x value, right? So I want to solve for x, the way I put them in anyway. And there's what it says. So it says that between these two is 0.41243, I ran out of room, 0.412. So not exactly in the middle of these two, but if you do a linear interpolation between this data point and this data point, then we would get 0.412 at a 0.16 y value. All right, so I can take that. So we also need our z equation. Well, before this calculator goes off, let's see. Z equals 0.41243, right? We also know that z equals x minus mu over standard deviation. So I've got an equation where x, this is x right here. That's the number I'm trying to solve for. So x, I don't know. z is 0.41243 equals x minus the mean we said was 42 divided by standard deviation we said was 7. So I can solve this equation for x. Let's see. If I take the 0.41243 multiplied by 7 and then add 42, it gives me that x equals 44.89, which looks reasonable. I said that, when I drew it closer to the 49 spot here, but it's between 42 and 49. That's where my number is, pretty much at 45. So it would say that with a mean of 42, standard deviation of 7, anything less than or equal to 44.89 represents 66% of the data. So 0 to 50 plus 16 to get to 66%, and that corresponds to a x value down here of 44.89. All right, now let's see if we can do this same thing in Python. So it's going to take the same approach, except that obviously we don't have to worry with the chart. It's going to use let's get Python on the screen. Similar function, like here we did the cumulative density function, where we have the we give it an x value and it gives us the area under the curve. Well, we're going to do similar to that, except we're going to give it a value, and it's going to give us the we're going to give it an area under the curve, and it's going to give us an x value basically. So this is going to be the ppf, percent point function. So I don't know if you'll remember all these names. We have CDF, PDF, and ppf, and they each do their own thing. Maybe we'll write that down in a second when I remember it. All right, so why don't we just take what we already have here. We already have we have to change this to a mean of 42, standard deviation of 7. We can leave this alone if we want to. That's certainly going to be a large enough range for this set of data. We could actually tighten it up to much smaller than that. Looks like, let's do negative 100 to positive 100. Should be okay. All right. We generate the normal curve, create a plot, draw it, and then we don't want the cumulative density function. We want the percent point function, and we want to correspond to, I think we need to put decimals in here. Let me make sure that we need decimals and not the percentages, but I need to check because I don't remember. I guess we could just put one in, and yeah, we need decimals. All right, so instead of 66, we'll write 0.66. So it does want the decimal version, not the percent version. And then it'll print it out. So let's see if that works. Oh, it won't work because I see a problem. I put a comma right here. Try again. There's our little plot, same one that I drew. When we close that, there's our 44.89, which is actually what we got. So even our little interpolation was close enough to give us the same value on our chart. By hand, we got 44.89. Python also gets 44.89, and then it's got a whole lot more decimals than we had before, but same number. And that's with interpolating on the chart. Now, the range we interpolated was pretty small. We interpolated between 0.41 and 0.42, so that was relatively small, and a linear approximation between those is close enough. Now, if we were interpolating a larger range, then maybe that would not work as well. So we can do all the same things we can do by hand. We can do in Python, and in Python we can get, nicer graphs. We can actually, you could go in and do some more details on this, or create it nicer. We don't need all this space over here. It looks like we can go from 0 to 75. If we want to do that, we just go change this to 0, change this to 75, and it'll give us a close-up view of what range we're actually interested in. We could put a vertical line on there if we wanted to at the 44.89. If we could do a lot of different fancy things to make this look more like what we would draw. But it's not terribly difficult. You just have to get in your mind what the probability density function, cumulative, and the percent point, what each one of them are doing for you. So the probability density function, it returns the y value given x. So on our graph, it gives you the height of the graph. So you really just use it to plot the thing, is all we used it for. CDF gives you the area under the curve, so that's the cumulative density function, but it goes from negative infinity over to whatever value x you give it. So sometimes you'll have to figure out, like if you wanted to know this area, then you'd have to do 1 or 100% minus the CDF to get this area, which, sometimes you have to do that. And then the PPF does the opposite. In fact, sometimes it's called the inverse CDF. So you give it an area under the curve, and it returns the x value that corresponds to that area. Again, from negative infinity over is what it's assuming you're going to give it for the percentage area under the curve. So those three, mainly the CDF and PPF, will help you do the same thing that we did by hand in the charts. There are similar things for the t-test, where instead of doing a normal distribution, and we can it's still a normal distribution, but it's a t distribution, where the idea is that you have a really small data set and you have some uncertainty about how well it represents the data because you didn't get to collect a lot of data points. And you can do similar things. I think we'll save those for later, and then we'll go on and work on our strain gauge right now. But just because I'm running out of time to get to the strain gauge, and I want to get to that, at least this stage of it, so that we can work on it a little bit. So let's look at strain gauge. Let's see if we can get mine. I've already lost it. Here it is. All right, so we're going to have to zoom in on this guy. It's really small. So inside here, see if I can get it out. Right. It's in here, and then it's inside another little sleeve, which I don't know how it, oh, there it is. All right. So I'm trying to get it with tweezers just so I don't get oils and everything on it. But there's the strain gauge. I don't even know how well it shows up. That's as far as, oh wait, is that a far? No, I can actually zoom in one step closer. It's probably going to get kind of blurry. But there's the thing. See if we can make it focus. Maybe, I don't know. But these two little pads, you're going to solder onto. In fact, if I get a multimeter, let me see. Get a multimeter out, then I can maybe measure the resistance of this thing. These things, I think, are around 120 ohms. Now you can kind of see how small it is. Yes, mine is 120. It's kind of scooting around everywhere. 120, it's exactly 120 ohms according to my multimeter. There is one thing to be careful here. It is a little bit difficult to tell one side from the other. So it does have a front and a back. If I can get it picked up. I don't know if I can pick it up. There we go. The back side's a much duller. So you can see there it doesn't have as shiny of a coating. So when you're putting this thing on, we're going to super glue it onto the beam over here. You do want to make sure that you have the shiny side up, otherwise you won't be able to solder to it, and it won't do anything. So you're going to have to solder wires to these little copper pads. The strain gauge itself is this part over here, and I just don't know if you can see what's on it, but we can probably draw a picture of it if I can't get it to show here. Let's see. Wow, that's my hand. If I can find it. There it is. Oh, you can kind of see it every now and then. So all those little lines back and forth are the strain gauge. So how it works is it's basically a wire. Let's get it off of me. Very tiny little thing. And they actually make smaller ones and larger ones. All right. Let's zoom back out so we can. So there it is. What you've got in here is the two pads that you're going to solder to. And between them is something like this. Like that. So it's just a wire. And in this particular one, the resistance here is 120 ohms when it's not strained. And oh, I got to get stuff out of the way here. Got too many, got Python in the way and all this stuff. Let me clear out. You might remember, I don't know if you remember or not, I have to look it up all the time, but the equation for a resistor, if you were to calculate its resistance, R equals rho, that's the resistivity of the material that the resistor is made of. Length, so that's how long the resistor is. You know, in this case, it would be all the length of this thing over A. And this A is what's important. The A, or at least for a strain gauge. The A is the cross-sectional area. So what you have to imagine now is as you strain, so this is going to be mounted maybe on top of this beam, and as I strain it, so I tension on top, then this thing is bonded to it, super glued to it, and it's going to get longer also. So if it gets longer, then the area, the cross-sectional area of this resistor has to get smaller. So I change this denominator, get a smaller number here, resistance goes up. If I do the opposite, if I mount it on top here and I put this beam in compression on the top, then it squeezes all this together, and the length might change a little, but the area, the cross-sectional area, is going to dominate this equation, and it will, in this case, get larger because you squish it all together. The area is going to get larger, and it will decrease the resistance. And that's what I'm picking up on. I'm actually picking up on the change in area that has to do with if I'm stretching this strain gauge or compressing this strain gauge. All right. So to get this thing on, now there's very specific ways to do this, but we're going to have to, obviously I'm not in a lab setting right now, so we're going to be a little less specific, but you should have a couple of things. A little aluminum bar to put your strain gauge on. Some tape is going to help. It's not totally necessary, but it will help. We need the strain gauge, and we do need to make sure that we are putting it the right side up. Now, this particular one is pretty easy to tell the top from the bottom. The bottom is very dull compared to the top. I don't know if you can see that on the camera, but I can see it easily here. And I've got some IPA, so this is just isopropyl alcohol. We'll use that kind of as a cleaner. And I need a little piece of sand. Oh, right here. A little piece of sandpaper. So I'm going to basically clean up a spot on somewhere near the center of our beam. It doesn't have to be the exact center. The beam we're going to build is basically a cantilever load cell. So it'll be held somewhere, and the force will be put over on the other end, and then we'll measure the strain on the top of the beam. So I'm going to pick a spot somewhere in here, And all I'm going to do is I'm going to put a little bit of IPA on there and just try to sand back and forth to get this thing, get some of the oxidation off of it. Oh, one other thing, you need something to wipe all this stuff off with. So, let's see. Now there are actual like cleaners and activators and all that that you can use for this. I'm being, doing what we can do right now. So we're just trying to get it. I'm not like trying to sand it smooth or anything. I just want to get it clean. Where I'm going to mount this strain gauge. That's probably going to be plenty. I'm going to squirt it one more time with IPA and then wipe it down. And notice I'm only wiping in one direction so that if I drag any material into it, I'm dragging it from a clean spot. I'm not like smearing it all back and forth. All right, so now we've got, and it probably doesn't show up much on camera. It barely shows up and I'm sitting here looking at it, but I've got a cleaner spot than other spots. So what I want to do now is I want to put the strain gauge in that spot with the pad side up so that I'll be able to solder to it later. And I want the pads going that way. Now the pad direction only matters because I'm going to have wires coming off of it, and I'm thinking of this side being the part that gets clamped down and the load is applied to the other side over here somewhere. You do want it, in this case, we want it parallel. You don't. There are some instances where you have multiple strain gauges and you intentionally put them at 45-degree angles, but we're not doing that. We only have one strain gauge. One of these is, I don't know, you can probably get a strain gauge for a few dollars. They're not terribly expensive. They can be more expensive, but a few dollars is typical. So I'm going to try and get it straight as I can and centered up there, or something like that. Then I'm going to take a piece of tape. So this is just the clear cellophane tape, and tape it down. All right, so this is not at all how you mount it. This is just what I'm going to do now is I'm going to peel this tape up and hopefully take the strain gauge with it. And then now the strain gauge is kind of indexed when I can put it back exactly where it came from. Now, they do make specific strain gauge glue. I do not have any here, so I have some super glue. This is a gap filling super glue, so it's thicker. It would be better if I had a thinner one. I really don't want to measure the strain in the glue, so I don't want a thick layer of super glue, but this is what I got. So this is what we're going to use. And I'm just going to put it kind of, this strain gauge is laying right there. I'm going to put this right where the strain gauge is going to lay, a little dot of it, and then I'm going to put it back down and hold it there for a little bit. Now, if you had some activator, they do make activator for even this kind of super glue that kind of instant cures it. If you somehow have access to actual strain gauge applying tools, then you would have activator and a glue. The official glue is basically cyanoacrylate, which is super glue. So I'm just going to hold this for a minute to make sure it sets up, and then hopefully what we'll be able to do is peel the tape off, leave the super glued strain gauge on, and that's mounting it. Now, if you're a little unsure of if your glue is set, you can leave it to set for hours or whatever before we go on to the soldering phase. This one probably says something like 10 seconds is all you have to hold it. It's covered up with a label, so I can't read it. But typically it's like 10 seconds or something. Let's see what we have. So now we would remove the tape, Yeah, there we go. All right. Now it is all still super gluey, so let's see if we can get some of that off of there. So there's probably still uncured super glue. It'll cure in a second while we work on the next part. So now we've mounted it, and that's going to be one of the key parts, because we want this strain gauge to experience the same strain that the beam is experiencing. Because what we're going to do is, if we can figure out the strain in the beam, then we can use beam deflection equations to back out what the force that created that strain must have been, assuming we know things about the geometry of the beam, the material. This is 6061 aluminum. So if we know E, modulus of elasticity, moment of inertia for the beam, if we know all that kind of stuff, and we know the strain in there, then we can back out the force that must have created that strain. We can, oh, actually, I guess we could do the stress, and then Hooke's law will tell us the strain, and the force will tell us, or the stress will tell us the force, and back it out that way. We'll get to that later. All right. I'm going to get some wires. Now, these wires I actually don't want to be big, bulky wires. For one thing, they got to solder to these little pads, so that's going to be tough. Another thing is I don't want the wires breaking off, so I actually want some flexible wires. I've got some little ribbon cable here that's going to probably work fine, except it's all taped up. And I don't see the edge of where the tape starts. Let's see if we can get it off of there. There we go. At least there's some of it. I want to have, and I don't need all these, I only need 2 wires. There's different ways you can hook up strain gauges. These particular ones just have 2 solder points, so we're going to solder 2 wires. Maybe we'll do the white and black wire. And I want to leave enough length on it so that I can plug it into a circuit. So maybe I'm going to cut off something like, well, let's just peel the white and black part out. Come on. I can't get it started. There it goes. I'm just going to peel out these 2. They'll be plenty flimsy enough. They won't create problems, hopefully. And we'll cut those off. And now I've got this little guy. And I can solder it on here, and the other end I can, now right now it's going to be tough to plug this end into a breadboard, so I'm going to have to go in and tin the ends of it, or maybe connect it to something that's easier to plug into a breadboard, but we'll worry with that part later. Right now we need to get this guy kind of in this position and these wires stripped back so that we can actually solder. This is the part, the soldering part, where you can make lots of mistakes. I guess the first mistake would be, you know, if we glued this strain gauge upside down and we don't have any pads to solder to. That's kind of hard to overcome. You can sometimes, if you did that, scrape through the backside to get to the solder pads, but that's usually not going to work. But you could try. The next thing you could do, assuming you glued it in the right way, is that when we go to solder on here, we can burn the pads off, and then you pretty much, so let me show you. Zoom in closer to this guy. If you burn off a pad, there is a little bit of a pad underneath this film right here that would still be left, and you can scrape the film away and solder to that if that ever does happen. Hopefully none of that happens though. And then the last thing, well, I don't know the last thing, another thing that could happen is you could get everything soldered in place, and then you somehow grab the wire. You grab the wire and you can rip it all off. So we're gonna tape our wire down once we get it soldered, or maybe before we get it soldered actually, so that we don't accidentally yank it up and pull the thing off of there. Strain gauge. All right. Now let's see if we can get a little bit of solder on our pads first. I do have some flux paste here that I'll try and get in this area. Don't want a big giant glob of it, but I'm afraid that's what's going to happen. There we go. Get that in there. I've got my soldering iron heating up over here. I've got some regular solder. This is rosin core solder, so it has flux in it. Here's the soldering iron tip. I'm just going to clean it off a little bit. So I've got one of these. All right, so it's clean. We're going to wipe it off with this to see if I can get any. Look, there's always something left, right? All right. And then I'm going to tin this tip. Right, and then we're going to try and get, I should have switched over to a smaller tip though. This one's a little bit big for these little tiny pads, but we're going to try and get a dab of solder on the pads just to give us a starting point. So I've got some little tinned pads there. Let's see if we can tin these. I should have gotten something to hold this in place. But let's just see if we can get some solder on here. So if we start out with solder already on our wires and our pads, then we don't have to worry quite as much about the getting solder and wires and pads all in one place at one time. So I'm just having trouble because I don't have any helping hands over here. All right, so now we have soldered on here. That one's a little blobby. I don't like that. Oh, I guess that's another thing that could go wrong. If you get too big of blobs, then you can actually connect them together, and that's going to be a problem. All right. Now I've got these a little bit long. I'm going to cut them back to be just, I don't know, a few millimeters long. Just like that. Now white and black, that doesn't matter as far as left and right. This is pretty much all resistors don't care if they are one direction or the other. So I'm going to put it in place. And then I'm going to go ahead and tape it down in place. I'm using, what am I using for tape? I'm just using some 3M tape, kind of like duct tape, but really sticky. So let's get it more or less in place, something like that. Make sure that that wire can actually reach. It looks like I've got them cut a little bit different. I don't know how I did that, but somehow I did. So this will be some strain relief over here so that hopefully if we ever pull on the wire, we won't pull the strain gauge off. So that's what that's going to be. Now we're going to try and solder onto that. I will have some solder nearby, but hopefully just do something like this. And same thing over here. All right. Then we need to go to the other end over here, cut these apart, and actually test that we got it soldered and have connections. So when I measured this before, it was kind of off the screen. You couldn't see the multimeter because I was zoomed in so close. But when I just measured the strain gauge, it was at 120 ohms. This wire doesn't have a whole lot of resistance, so it should still be more or less at 120 ohms. Whoops. At this end. All right. So let's get the multimeter back and connect these guys. And there's no way we're going to be able to plug that into a breadboard, so we're going to have to either solder some ends onto it or at least tin these so that they're stiffer. But for now, all we want is to see if we have. Yes, well, it's 120.3 ohms, but that's okay. Because we're going to calibrate it anyway, so we just need it to measure. Now let's really test it and see if it changes when we, look at that. More resistive when we put it in tension, less resistive when we put it in compression. That's what we want. So that's a really tiny change that next time, I think we'll do it next time, we'll come in and we will build our equivalent of this chip right here, or this whole circuit right here. We'll build it without some resistors, just some probably, I think 100 ohm resistors is what we have in our kit. I have to look and see. But whatever they are, we'll build a little resistor network and put this as one of the resistors in that network, be able to detect a tiny voltage like we've been doing. We'll have, that tiny voltage is very tiny, so we'll have to amplify it. So we'll have to do a little bit of circuit building with an op amp, which we also have in our kit. And we should be able to get a voltage over to the Arduino, which is what we've been doing with our thermistor and our photoresistor and all of those things. And at that point, we can start to do the same type of stuff where we do an analog read and we have a value from 0 to 1023. We can interpret that and figure out what it means as far as this resistance change and what that means as far as a strain and a force that causes that strain in our beam here. And we've created a little load cell at that point. I think that's enough for today. We actually have more time, but I think we actually covered all that I planned to cover. There is a little bit more with the t-test. Oh, wow, you said that your strain gauge already has 2-inch leads that solder to it. Wow, that's way simpler. And it also says that you attach 3 wires. So sometimes you put 2 wires on one of these. That's okay, because there are some 3-wire strain gauge setups where it's expecting to have 3 wires on the other end. So if you have a strain gauge wire set, a lot of times that wire set will have 3 instead of just 2. I made this out of just ribbon cable wire, so I only used the 2. But if you ever needed to make this one into 3 wires, I could just split one of these into 2 on the other end. But the 3 wires is just because a lot of strain gauge wire, if you get the actual strain gauge wire, it has 3 strands in it, or 3 wires already bound together. And so you actually just put 2 of them on the one pad and 1 on the other pad with this kind of strain gauge that only has 2 pads anyway. So I just didn't even bother to, since I could pull off and just have 2 wires anyway, I just put 2 of them on here. We're going to wire it up in a 2-wire arrangement, but there are 3-wire arrangements and other types of arrangements. Sometimes you actually have to send a voltage to excite the strain gauge. We don't need to do that for this. We're using it really as just a resistor. And it's good. So it says that it already has lead solder to it. So you don't have to do the soldering part then. You just have to do the mounting part. Still relieve this, the wire. You said that they're pretty short, 2 inches. So then all it is soldering longer leads on the wires that you already have on there. So that's actually going to be a little simpler than what I did here. But I think this is going to work. Our multimeter said it was working the way we wanted it to. That's what you want. Once you get it mounted and everything, hook it up to your multimeter, switch over to reading resistance, and you should be able to flex the beam. It is aluminum, so don't flex it to the point of yielding it, but flex it enough and you should be able to see the 10th spot move on your multimeter go up a couple of tenths of an ohm or down a couple of tenths of an ohm. All right, so work on that. I do need memos from your team about what sensor you're going to use. That's due on Thursday. This is for the bigger project, the sensor for the bigger project. I need basically just the sensor model number. Be as specific as you can with all the details of it, but the whole memo is, a page or less. What you're going to test, what your hypothesis is, what do you think the data is going to show, who all is on your team if you have more than one person on your team. And I do have a list I've tried to keep up with the list on Moodle on class 20 for the sensors that have already been claimed. Some of them, I'm letting them be 2 versions of each sensor just because we have more teams than normal. So some of them have a 2 beside them. That means that 2 people or 2 groups have chosen that sensor already. So they did tell me that you could check sensors out from IESB, the store over there. You can also buy them from the store over there. You can buy them online. There are some sensors in your kit. There's some sensors we haven't talked about yet in your kit. You have the strain gauge. We have the Hall effect sensor in your kit that we haven't used. We touched on the photo resistor, but we didn't use it for anything, although I think people have already claimed that. I don't know if your kit came with any other sensors or not. But we'll get to the Hall effect sensor in a little bit, and it's easy enough sensor to use. There might be an infrared sensor in there, or you might have one from your freshman kit anyway. Let me know as soon as you know what sensor you want to use so I can mark it off as there's a group using that sensor. I think that's all the stuff coming up. A lot of what the rest of the quarter is we look at some sensors. There's some more statistic stuff. We have to do some more with the t-test and how we actually use that for something. We haven't even talked about the t-test. We've only talked about the t-distribution. We have to deal with some confidence intervals and that uncertainty. Remember at the beginning of the quarter we talked about how there was a certain uncertainty associated with measurements, and we have to talk about how to even arrive at that. And so there's a couple of more things like that left to do, but a lot of the very end of the quarter is working on your project. All right, I think that leaves us in a good spot for Thursday. We'll come back and do a little bit more statistics, and actually I'm not sure what the other stuff for Thursday is. Let's see if I have it pulled. I don't have it pulled up, but we'll do some other interesting things on Thursday. Oh, here it goes. It is, uncertainty, which is what we just talked about. So that's related to the statistics a little more. But we'll also do a sensor as well, or a tool, if not a sensor. All right, I will see you on Thursday. Let me know if you have any questions. If you do have problems with your strain gauge, then there are a few things you can do to try and solve them, but a lot of them mean you have to get a new strain gauge. You only have one in your kit. And there's a lot of stuff that you just can't fix on them. They're so tiny. There are other strain gauges. I think there are even some in the vending machine in IESB. There used to be anyway. All right, I will see you all on Thursday.